welcome to our today's MIU. I'm Olaf Rende. I will guide you through the session today. Please note this presentation will be recorded, so by attending, you agree to our privacy policy linked in the action notice, and we asked you to switch off your camera and microphone so that we have a clear presentation. Feel free to ask any question in the chat. We will answer them after the talk. And now let me introduce our today's speaker, Emin Nakilji, and with his topic on advanced workload forecasting for logistic nodes using Bayesian networks. So, Emin, the stage is yours. Feel free to begin.
Thank you, Olaf. Thank you for the introduction. Yes, welcome you all. Today I'm going to be talking about one of our projects called Workload, which stands for Beidseit-Prognose in the Logistik. All right, let's just begin. Here is the agenda. So a little bit of a background about the project, and then we dive right into the details of the project. All right. So Workload, also formerly known as Kikli, is actually a follow-up project of another one of our projects called Lilia. Since they both tackle the same problem, so let's just start exploring the problem at hand, and I'll get into how they differ. So during these projects, our main project partner was HCS Depot, which is a company that owns and manages empty container depots, where we can store the empty containers. So on the right side, you're seeing this schematic representation of a part of hinterland logistics that is related to empty container depots. Vessels are bringing the goods in the containers. They're being delivered to the target factories or target places, and then come the empty container depot in place. After the deliveries, you end up with all these empty containers. So they're transferred to the depot, mostly using trucks, or LKWs also known as, when there is a need of empty container, so then they're transferred to be loaded, and then same old story goes on, but with the export, not with the import. So it's actually just works just fine. There's no problem. But the problematic parts start with the uncertainties and miscoordination inside the workflow. So these enhance situations where overload or underload regarding the workload of the empty container depot, or any logistic nodes for that matter. So if there's a system, what we're thinking, if there's a system where we can, predict, foresee such anomalies, meaning higher or lower workload than expected, or in regular, so we can control the effects of such uncertainties may have on our planning, our working conditions, our workload. So we want to see whether we can come up with a system utilizing data sharing from multiple sources, of course, and AI-based solutions to optimize the situation. And I needed to mute one more. Yeah, so you can see the general structure of the system. Collecting data, running our forecasts, and we publish these predictions for interested parties. So main difference between the projects is, as you can see here, is the methodology. So the forecaster is an AI-based model. It's made out of artificial neural networks. We train an AI model using the collected data, and we use a trained model for forecasting. That's the main idea, right? And though they both use the same input, data, the same input, they generate the same type of forecast, which is the hourly expected truck rate for the given depot in our case. The way they go about it, generating this predictions are quite different. The one method is a traditional method. It's trained using like a traditional methods, which I will refer to as deterministic methods, and then generates using the same methodology. On the other hand, we have Workload, which follows a probabilistic approach. That's just to give you guys the general understanding of the situation. I will get a bit in detail as we follow on with the slides, but to start with, that's the main difference. I want to go on with the use case, in our use case. So this is the animation of a workload in empty container, of course, simplified. So truck comes in to the gate with or without an empty container, depending on if it's going to go to loading, depending on the task. If it's going to take the container and use it, they're going to use it for loading the packages, or there's already an empty container, they just want to put it in the depot. As the truck goes through the passage or the gate, there's an automatic generated tag. We call it gating tag. This is important because it's our base data that we use for training as well. So truck waits until the documents are generated, and then moves on to the area of interest, loading or unloading, depending on the task, as I mentioned. So when the task is complete and the last checks will be done, the truck is ready to go. As soon as it leaves the gate, there is also another tag that's automatically generated. That's the gate out tag. That's also one of our base data points, let's say, of our database. So the whole process, therefore the time spent during that process between two gates or two tags, however you want to call it, is what we call dispatching process or handling process, and therefore dispatching time and handling time. This is also another prediction that we do along with the hourly truck rate, is the average time spent handling trucks in a given hour. So we have two predictions done or generated simultaneously. So speaking of data, data sets. Yeah. So our main data set consists of container type, which day it is that the helicopter arrived at the gate, whether the truck is here to unload or load, and also the gate tags, gate in and gate out tags. But in case of Workload, we also have obtained another data type from HCS depot, which is a truck appointment system. So it's basically truckers can call beforehand and let the depot know about their possible arrival time. Of course, it's not always accurate, but it usually has a lot of missing data. But we found a way to work it, since we want to see what the probabilistic approach is going to bring to the table. It kind of helped a lot, as you guys will see with the results. So I mentioned the main difference is the methodology. So here I have like a simplified graphics to explain the difference. So on the left side, we see a traditional deep learning model using deterministic backpropagation method to learn the input and output mapping from the given data. Bunch of iterations, you will have an approximate mapping between the input and output. Where they fall short is the situation where you need to amount to the uncertainties in the model or in the data, or cases where the data is full of missing data, or you have limited data. In this situation, people use Bayesian neural networks or Bayesian learning. That is the probabilistic approach that I was referring to. You can see the weights between the nodes are not scalar on the right side compared to the left side. The left side is the deterministic one is the scalar values. That's what you train and learn. But on the Bayesian side, it's rather distribution. Its learning process is based on Bayesian inference. So it's a method of just statistical inference, so to speak, in which the Bayes' theorem is used to update the probability for the hypothesis. So as when we have more evidence and more information becomes available, you kind of update the probability. One of the main advantages in our cases as well is that now we can model the uncertainties inside that learning process by just simply specifying a priori, just prior condition. That's why it was important. We've seen a difference when we put the data from the truck appointment system, which gives us some kind of a realistic, even though it was missing data a lot, but a little bit of more realistic priori, like prior condition, compared to not using such prior conditions. So we incorporating that prior beliefs or information about the data. You can also do that with the model parameters, but we haven't. But we just use the the prior beliefs regarding the observed data. So you will have like a posterior condition that is affected by this prior, and it kind of quantifies the uncertainty, which at the end you kind of model the uncertainty into your learning process. Since we have prior conditions in the equation, and then we have like a uncertainty incorporated into the learning process, you will always end up with different values given the same input. Whereas in the traditional approach, you have a model trained on, and you give an input, ask what is the expected truck rate for the next week, Thursday at 10 p.m. or 10 a.m. Every time it's going to generate the same output, no matter what. But in a Bayesian approach, Bayesian learning, it produces a distribution. And depending on the changing conditions of the priori, you will have always a different answer. So to address that, there is a thing called Monte Carlo simulation, which is just run in multiple simulations and average out the predictions, and that's going to be your final forecast, final output that you're going to publish. So Monte Carlo simulation is just used to predict the probability of a variety of outcomes when there's a potential for random variables. In our case, that was the modeled uncertainty into the system. It kind of helped explain the impact of the risk uncertainty, which was a good fit for our case as well. So what did we get? What are the results? Was there an improvement whatsoever, or we were just wrong about incorporating uncertainties? So as it turns out, it does affect quite a lot regarding the performance. So you're seeing the performance comparison between the models in two tasks, truck rate, predicting the outer track rate, and also predicting the average dispatch time. So green bar is Lilia. It's the initial project. We have blue, Workload, and gray is just Workload model, but with addition of the tracker appointment data. We wanted to see the hypothesis was true, if this priori can affect our prediction. So just a quick explanation. Yeah, you see R squared. It's just a metric used to evaluate prediction. It's kind of one way to calculate the distance between your predictions and the expected value. We use R squared because it's kind of quite realistic, because if you have value of 1, which means that was a perfect fit, that's the best you can get. You can just get the perfect fit. But being the worst side, you can get really, really worse predictions. So the window for the R squared value is between 1 and minus infinity. So you can get pretty worse. So that was the realistic part. That's why we used it. You can also see in the handling time, there are some minuses as well, just to explain the situation. So the results are interesting, actually. So when you can see that adding the uncertainty provides quite a benefit to the system in both tasks. We also see the scale is moving to the truck rate prediction task from the dispatch task. We see a poor performance of dispatch task when we add trucker information, because our hypothesis was that it's a result of trucker appointment having more priori regarding a truck rate, but does not bring anything to the table regarding the average handling time. All this average handling, just the information is only on the base data. So that was our hypothesis as well. But we've seen the improvement regarding the truck rate. So let me just put into the graph how will be the predictions would look like in our predictions. You are seeing this is the orange line as the real values, and the blue lines are the generated and prediction values. So you can see the better prediction. We have better prediction with the probabilistic Bayesian methods. It's not an approximation function that you can see for the Lilia. It's rather a function that is approximated, by the training of the given data. But the Workload case, you can see the ups and downs, which is really important because we want to try to address the overload and underload, which is ups and downs in this graph. So that was our like a success regarding applying probabilistic methods. this was the graph is for truck rate, and we have like an overall rate, like an error rate, meaning minus plus 5 trucks for the Wapolo case and 6.5 for the Lilias case. Considering the lowest truck rate per hour is like 20, and in average case it's more than 40. So you have a minus plus 5, that's good. But also, as I mentioned, the important part is figuring out the ups and downs, which is the main overload and underload situations. Yeah, so what we achieved, we have like a proper stable forecaster now that provides more realistic predictions. And it also gives an opportunity to update the forecaster, because when you have like a updated information, you can just update it to priori, and then you will have update. You have an easier way to update your forecaster. So what are the numbers? So we have 6.7% increase in performance regarding the hourly predictions of expected truck rate. And when we add the appointment system, it goes up to 15%. But the dispatching time was quite a lot, because you're getting minus performances. It was worse than just randomly selecting values. And so we have like a 103% of increase regarding performance when we add the Bayesian approach. Also, this one plus side is we have now faster predictions. The prediction using the probabilistic approach tends to be faster. That means less computational power. And just to give you the numbers, it's just from we were taking 20 minutes to go through all this prediction situation using the tradistic method. It was 20 minutes. It took us 20 minutes. And with the Bayesian method, we just need 7 minutes to go through all that and result. We have the predictions of the model. So that's quite an improvement. What is waiting for us ahead? So we want to extract more relevant data from different data sources. There are some sources out there, a couple of them open source, most of them not. Container exchange data from that is available that just gives information regarding the container traffic in the given ports. Hamburg, Port of Hamburg is one of them. There's also salientness from HLA, HHLA, that kind of gives the expected vessels coming in the upcoming days. So it's kind of give you like a forecast as well. It's like the trucker appointment system, but for vessels. It's kind of, you want to try that as well. We haven't really got into that, kind of examining that data and the effects it may have on our system. That we can do. And the uncertainties, as just shortly mentioned, that we just used uncertainties regarding data. There was also the model part, that the calculation that you do with your model. There is also the uncertainties that comes with the model parameters. We haven't modeled that in our system in research, but it is something we want to explore as well with the further research to see if it is how it would affect our predictions. Yeah, that's about it. Thanks so much for the attention. If we have any questions, I'm happy to answer them as well.
Yeah, thank you very much, Emin. And as mentioned, if you have any questions, I don't see any in the chat. Just raise your hand and we can answer them directly. So otherwise, I have a question for you, Emin. So is there any difference between updating the model? So what is the effective or what is the performance influence of updating the traditional model to the more modern or more probabilistic model?
Yeah. So with the probabilistic model, if you want to update your model that you have like a new current data, you have to start all over with training, and you train a new model with the new data. Regarding the probabilistic model, you don't have to go through all that, because we have like a priori that kind of gives the hint of this prior conditions. If you have like a new observed data, you can put that into your system as a priori and you will have like a more easily updatable system that is more up to date. And yeah, so that's the main difference. One is quite user friendly, so to speak, to include the up to date data. The other one, we have to start all over from the start.
Okay, thank you. Any other questions from the audience?
In case further questions, this my email address. You can reach out to us in LinkedIn, front of HTML, or to my email address as well.
Another question which came to mind is, you mentioned the modeling of uncertainties in the process. Do you have a rough estimate how realistic the uncertainties are in this modeling?
Yeah, it's we wanted to test that as well. How to scientifically put the realistic, like how realistic it is. It's really tough to estimate and put into numbers, but we can only just see the effects that it was realistic. It was the fact that the appointment data that was kind of the main change between not two Bayesian training period. One didn't have this extra priori, being the trucker appointment system, that adds another kind of condition. And we've seen when we put that into equation, we've seen quite an increase with the results, especially the trucker, since this trucker appointment gives information about the truck rate. So we see quite an improvement on that side as well. And also we know it's kind of a scaling change in the scale, because when we put much scale on the truck rate, and then we kind of lost the interest in the priori, in the handling time, the dispatch time. We saw the effect that as well. We can say it's quite realistic. It's definitely more realistic when we put this real prioris compared to other methods that we tried in our project. We can see the real conditions being applied as uncertainties, and it kind of generates the predictions more accurately due to that we assume.
Okay, thank you very much.
Thank you.
So, since there are no further questions, I would like to thank you again, Emin. And I want to announce that we will be on a summer break from now on, and the next exactly, and we will continue in September 2024. So see you then.
Thank you, Olaf. Thank you all for joining. Yeah.
And have a nice Friday. Have a nice weekend. Have a nice summer. See you. Bye.
Thank you. Bye.